Welcome back, students. In this video we are going to discuss one more theorem of electrical engineering, that is Norton's theorem. This theorem is basically similar to our Thevenin's theorem that we had discussed in our earlier videos, but there are a few differences as well. This theorem was given by Norton in 1926, that is 43 years after Thevenin's theorem, and it is again related to the linear two-terminal circuits. And it is solving the same problem, like if we are having any kind of linear two-terminal network, that is connected across any kind of load, and the load is a variable, and if we want to find current, then according to the Norton's theorem we can replace it with one current source in parallel to the resistor that is called as Norton resistance, and then we can have our load, that is R. So this is basically the statement of Norton's theorem. So if we can correlate it with our Thevenin also, according to Thevenin, if we are having any two-terminal network in which one of the side is fixed and the load is variable, like this load is a variable, according to Thevenin, what we had studied, this was according to the Thevenin, that was equivalent to a voltage source, what we called as VTH, in series with the resistor, what was RTH, and a load. Now if we compare these two, the difference between the Thevenin and the Norton's theorem is, Norton theorem calculation is in terms of current source, while as if we are calculating the Thevenin's theorem, your calculations are in terms of a voltage source. If it is a Thevenin theorem, the equivalent resistance that we are calculating across a load is in series, while as if we are calculating Norton's resistance Rn, that would be in parallel. So all the background knowledge, like why we use Norton's theorem, it is all same like we have already discussed in our video of Thevenin's theorem. So if you have not seen that video, I would recommend you to first go through that video first, so that you can have a background knowledge of what basically Norton's theorem significance is. So coming to the IN, how will we define the Norton's current? It is basically, if we are having a two-terminal linear network and we are having a load connected here, now what we have to do is we have to short it. Okay, so there are two steps to calculate the Norton current. The first step is we have to short the load terminals. If we compare it with our VTH, Thevenin voltage, we had to open the load, but if you had to calculate the Norton's current, you had to short the load. So while we short the load, the second point we have to note down is we have to calculate the current across load terminals only. It means whatever current we will get now in this particular branch, that short circuit current is nothing but your Norton current. So the second parameter is Norton resistance. So what is Norton resistance? So Norton resistance is exactly same as your RTH. So all the steps that we have discussed in our earlier video for the calculation of RTH, the same way we can calculate Rn. So I hope you remember all the steps. I will recall it for you. The first step was we have to open the load. The load terminals, they need to be opened up. Second step was we will replace independent sources by their internal resistances. If that means if we are having a voltage source, we are going to short it, and if we are having a current source, we are going to open it. If there is any dependent source, then we will not change anything out of it. They will remain a part of the network like a resistor does. And finally, we will calculate equivalent resistance across load terminals. So these steps are same as RTH. So these steps will give us R Norton. Now to understand these steps further, we should solve one problem based on Norton. So let us come to the problem. Let us solve the problem based on Norton's concept. Now if you will see at this, if you will look at this diagram is same as the one we had solved for Thevenin calculation. I will show you the note. So if you will look at our previous videos, we have solved this problem here. First with the conventional method, we had to again find here the value of current I. So we have used the conventional method and we got our answer as 1.5 ampere. Then we have solved this question using Thevenin theorem, and we got the answer as 1.5 ampere again. So let me begin with calculation of Norton current. So we know there are two steps. We have to short the load and we have to find the current across the load. We have to short the load terminals and we have to calculate the current across the load terminals only. So let us apply those steps. So I have to redraw the diagram with only one change, that is the load of 1 ohm will be removed from the circuit. Now had this been VTH calculation, the load would have been opened, but since this is a calculation of Norton, so I have to short it. So this short circuit current is my Norton current. What happened now, if we see these two, due to the short circuit, 4 ohm resistance will be shorted out because it is in parallel to the short circuit wire, so the equivalent resistance becomes 0. So my diagram is bit simple now. My diagram will look like this now. Now this is my Norton current. This is your 6 ohm, 2 ampere, 6 ohm and 12 volt. So my aim is to calculate the IN. So what I can do is, I can assume here voltage V1, I can assume the directions of current as per my choice, and then if I apply KCL, at node V1, I would get I1 plus 2 is equal to I2. Now if you transform the equation, I1 is 12 minus V1 by 6 and I2 is V1 upon 6, V1 minus 0 upon 6. So let us multiply both sides by 6. So we will get 12 minus V1 plus 12 is V1, or twice V1 is equal to 24, or we can say V1 is 12 volt. So this voltage is 12 volt. Therefore, what is Norton current? Can I say that Norton current is V1 minus 0 by 6? Or Norton current is 12 volt upon 6 ohm. So the answer is 2 ampere. So my Norton current is 2 amperes here. Now second thing is we have to calculate the R Norton, and I already told you it is same as the RTH calculation. So I will again repeat it, although if you have seen the previous videos, you should know what the answer is, what answer we must be expecting. So let me copy the diagram. So apply all the steps that I told you here. You had to open the load, you had to replace the independent sources by their internal resistances, and you have to find the resistance across the load terminals. So let us apply all those steps here. So we will get something like this, because the internal resistance of voltage source is 0 and the internal resistance of current source is infinite. So accordingly I am drawing this circuit, and load we have to remove, and across load the equivalent resistance is R Norton. So this is 6 plus 6 which are in series, that is 12. Then 12 and 4 they are in parallel, so it is 48 upon 16. So answer is 3 ohm. Now we are ready. Now we are ready with the equivalent circuit. This is my equivalent circuit. So I would say once your both calculations are done, we will come to the Norton equivalent circuit. So the Norton equivalent circuit was Norton current in parallel to the Norton resistance and then load of RL. So what is this for our problem? For our problem, all the values are now known to us. I Norton is 2 ampere. I Norton is 2 ampere, R Norton is 3 ohm, and the load that is given to me is 1 ohm. Now can I calculate this I? Because this is what was the statement of the problem. I need to find current. I need to find current across the load 1 ohm. So this load is now a part of the circuit, and this is current I. So I can use current division. So current across the load is equal to total current multiplied with other resistance divided by total resistance. So you apply all the values. I can say I is equal to 2 ampere into 3 ohm upon 3 ohm plus 1 ohm. The answer is 6 upon 4. So you again see the value is 1.5 ampere. So we got the same answer, the one we got by finding it using the Thevenin concept or by using the conventional way. So mathematically we are proving that this theorem is correct, this is verified, and this is one more way of calculating the current across the load that is variable. And again you see the significance of this equation. Suppose your load becomes variable. Instead of 1 ohm, you are changing your load to different values. Suppose it might be 10 ohm, it might be 50 ohm, it might be 70 ohm, it can be anything. So what is the only change we have to make in the general diagram of the Thevenin equivalent? This R might be changing. So if we see this particular equation, only this term is changing. The rest is same because I Norton would be fixed and R Norton would be fixed. So all values that you are giving here, you can calculate the answer in one go. So the same statement I had repeated in the Thevenin also. That is what the significance of Norton theorem is. We can calculate current across the load that is variable in one go. In our coming videos, we'll be discussing numericals which are based on dependent sources also, and that time the concepts that are used to calculate the Thevenin resistance or Norton resistance are different than what we follow here. So I hope this topic is clear to you. If you are having any doubts regarding this topic, you can mention it in the comments so that whenever the time is feasible, I will reply back to your comments. Till then, God bless you all, and thank you.